Okay, guys, welcome back. This is Mr. Allen's lecture for 14.1 gas law properties. And here we go. Properties of gases. Okay, compressibility. Gases can be compressed. The distances between the particles can be decreased by increasing the pressure on a gas. And so a measure of how the volume of matter decreases with an increase in pressure is the compressibility. Gases are highly compressed due to the large distances between molecules. Now I'll let you write that down, then we switch the page. Alright, solids and liquids are only slightly compressible due to the close distances of the particles in the first place. In fact, we generally consider them uncompressible because the distances are so small. All right, so for example, 1 mole of any gas at STP has a volume of 22.4 liters, which is quite a bit. 1 mole of water, however, has a volume of 18 milliliters. So think about this. If you have a mole of water vapor, so it's evaporated water, it's going to fill up 22.4 liters. But if you have that mole of water as a liquid, it's going to be 18 milliliters, or just about enough to fill up a cap, to the cap of your water bottle. All right, factors affecting gas pressure. Okay, the amount of gas. So as you double the amount of gas at the same temperature and volume, the pressure also doubles. Okay, the volume affects gas pressure. As you compress a gas to half the volume at keeping the same temperature, the pressure is doubled. And then finally, the temperature. As you double the temperature of the gas on the Kelvin scale at the same volume, okay, the pressure doubles. So we double the temperature on the Kelvin scale, the pressure doubles. Okay, that's about it for 14.1. I do, however, want to take this time to talk a little bit about Kelvin temperature. So you might want to get out a separate sheet of paper or find space on your notes so we can talk about that. Okay, here we are. We're going to talk about the Kelvin scale. And to do this, Kelvin is called the absolute temperature scale. So the Kelvin temperature scale. Okay, the Kelvin temperature scale is called the absolute temperature scale, and here's the reason why. Our definition of temperature is temperature. Okay, you may have always thought of this as the hotness or the coldness of something, but it's really more sophisticated than that. Temperature actually refers to the average kinetic energy of all the molecules in a sample. So be it a gas or a liquid or whatever that is, the average kinetic energy of all the molecules in a sample. And so we call Kelvin the absolute temperature scale. This is also known as the absolute temperature scale. Because the math that can be done with the temperature must be proportional, and if there is some sort of absolute temperature, in other words, if we have the ability to add energy at infinitum, we can also subtract energy. However, we can only subtract energy so far. Okay, kinetic energy from our notes in 13.1 is the motion of molecules, and remember, kinetic energy equals 1/2 times the mass of the molecule times the velocity. Okay, so in this case speed, squared. Well, you can go as fast as you want, but if you're going to go backwards and you want to try and reduce all of the kinetic energy, there's only so low you can go. And so velocity, the smallest velocity possible, possible is, sometimes I can't write correctly, is zero. Or the smallest possible velocity is not moving. So, if our smallest velocity, the smallest velocity that's possible is not moving, then shouldn't the lowest temperature, or shouldn't the temperature that represents no molecules moving, also be equal to 0? Well, that's the idea of Kelvin. Kelvin scale allows for molecules moving at near zero speeds. Well, if the molecules are moving at near zero, that means their kinetic energy is almost zero. And so the Kelvin temperature should be equal to, where Kelvin is approximately equal to 0 temperature. This moment right here, when the Kelvin temperature equals 0, this is called absolute zero. This is a very important concept. Okay, we like, it's actually really cool when all molecular motion stops. Okay, it's virtually impossible to get there. There are very recent studies that have claimed to have reached absolute zero, but I'm still personally a little skeptical on it. Or have actually gone beyond absolute zero, or more than negative, which I'm not real comfortable with, because I don't know how things can move less than 0. But the claims are out there. Okay, so absolute 0 is when temperature has absolutely no motion. Now, the Kelvin scale is based strictly on the Celsius scale, and here's how it works. Absolute 0 has been found to be negative 273.15 degrees Celsius. Okay, but if we reset this and we say, okay, well, then this negative 273 degrees Celsius is now 0 Kelvin, get it? Okay, is now 0 Kelvin, then we shift the entire scale of Celsius down 273 degrees. Okay, and so if we get our thermometers, let's draw some thermometers here. We've got a bulb, and then we go up. And up here we have a boiling. For water, we'll establish it for water. And then here we have a freezing. And voila, we make three thermometers. If we assign one of them to be the Kelvin, okay, so one will be the Kelvin. Okay, we assign another one to be Celsius, and we will assign a third to be, well, a third be Fahrenheit. All right. Water boiling is a physical thing. It's an actual event, and so it's going to happen on the same place for all three of these thermometers. And freezing is also a physical event. It is going to occur in the same place for all three of these thermometers. Therefore, absolute zero is also a physical event that's going to occur on the same place for all three of these thermometers. And since boiling is a physical event and freezing is a physical event, so is absolute zero. It is a physical event. It is when all motion stops. And instead of occurring at those spots, it actually occurs way down here. Way down there. Keep going. So it stretches to the bottom of the thermometer. And we have, at the very bottom, we have our absolute zero. As low as we can possibly go, down here at absolute zero. And this spot is at 0 Kelvin. It is at negative 273.15 Celsius, and it is at negative 459 Fahrenheit, degrees Fahrenheit. Okay? Now, we have ways of figuring these things out, and the way we do that is we establish that our Kelvin is equal to our Celsius temperature, whatever our Celsius temperature is, plus 273 degrees. Right? And we, from earlier math, and maybe not in this class, but you may have figured this out earlier, that Celsius equals 9/5 Fahrenheit plus 32. No, I totally mixed that up. Those two are backwards. That should be Fahrenheit is 9/5 Celsius plus 32 degrees. So, if we scroll back up here, okay, our boiling point for Kelvin is 373. Oh, I can't write right now. Is 373 Kelvin, is 100 degrees Celsius, and is 212 degrees Fahrenheit. We know that boiling is freezing is 32 degrees Fahrenheit. I'm sorry, that's freezing. Freezing is 32 degrees Fahrenheit. Celsius, we know it to be 0 degrees Celsius, and freezing is also 273 Kelvin. Okay, so these are the comparisons. All right, now a couple things to keep in mind. Remember that freezing is also melting point, and boiling is also the condensation point. That if you bring the vapor of a gas down to below 300, vapor of water to below 373 Kelvin, it will start to condense. The condensation point. All right, so back here down absolute zero, this right here, this is absolute zero at that bottom temperature. And this is how we convert from our Kelvin to our Fahrenheit. And the moral of the story is this. All calculations involving temperature must be in units of Kelvin. Otherwise, it doesn't work, and we start doing proportions, and we have negative numbers in there with the proportions, and the math, it's the only way the math works. Okay, so that'll be the end of the Kelvin temperature scale, that little supplementary lecture, and after that, we will see you guys next time. So it's P-Dog signing out.